This meeting is being recorded.
In the Chapter 19 electrochemistry worksheet, there are a couple sections that are included. The first here on batteries, which is good to know and is covered in the textbook, but you will not be responsible for any calculations that deal with either lead acid batteries or alkaline batteries, as shown here. But I just wanted to point this out since it is included in the worksheet. So if you have any questions about it, please feel free to ask, but it will not be included on your exam. So let's see what else from the worksheet may be included. So let's take a look down here. We see lots about batteries and fuel cells. The next topic on corrosion, that's also mentioned in your textbook, the use of something called a sacrificial anode to prevent corrosion for pipes underground. That's also mentioned, but again, you will not be responsible for either corrosion or batteries on your exam. But let's take a look at what you may see. This next topic and our last topic is on electrolytic cells, and we'll look at some quantitative, some calculations that we can do using electrolytic cells. So electrolysis, if you recall, is when we pass current through our electrolytic cell and we create a non-spontaneous reaction, or we force a non-spontaneous reaction to occur. So again, these are exclusive to these non-spontaneous reactions. So one of these is shown below, this non-spontaneous reaction. So we force electrical current through sodium chloride in this specific case, and we create molten sodium chloride in this reaction. So at the cathode, we are reducing the sodium ions that were melted to liquid sodium. And then at the anode, we are oxidizing our -1 charge chloride ion that's in liquid state to chlorine gas. So we can see these are both the two half reactions. And we're asked down here, do you think that we would get the same products if we were to electrolyze an aqueous solution of salt, so sodium chloride, AQ? Usually not, because water can also be oxidized to form O2, or we could reduce water to form H2, rather than ions of salt. So let's take a look at some of this quantitative electrolysis concepts below here. So current, we define current as the charge carried by one electron as this 1.6 to the -19 coulombs. This can also be expressed in amperes. So that gives us a rate of time as well included. So we're going to note this relationship here, that 1 ampere is equal to 1 coulomb per second. And we've already talked about the Faraday constant being this 1 Faraday is equal to 96,485 coulombs per mole of electrons. So using these bits of information, these relationships, we can actually calculate either the amount of time it takes to electroplate something, to deposit a certain amount of metal. That's one application of electrolysis, is electroplating. So let's assume that for our first example here, example 12. And we can also solve for the mass in grams or the amount of time. So either of those can be solved for using these constants and some information given. So we're told that we can determine the amount of charge, which would be the product of our current times time. So if we were to multiply amps times time, we would get current in amperes. And then we have, we can convert our amount of charge to moles of electrons. We know that 1 mole of electrons is Faraday's constant. We can use the half equations to know how many moles of electrons are being transferred between our reactant and product. We'll look at that. And then we can convert from moles of reactant or product to a final quantity, either mass, volume, etc. So let's take a look at this sample exercise here, sample exercise 12, and see if we can complete what they ask of us here. So we are asked in this question to calculate the mass of aluminum in grams that would be produced if we performed electrolysis on molten aluminum chloride here for 1 hour, and our current is 10 amperes. All right, so we're given time, we're given our current, that's abbreviated I, for those that haven't taken physics. And then we can also assume that our AlCl3, when that is molten, we would expect that to be a +3 ion and have lost 3 electrons. So we're going to use all this information here. This is our half reaction, rather. So this would, when it gains 3 electrons, this would be our electroplating, this solid aluminum. All right, so let's see if we can set this up. We were given time, current, etc. So what I'm going to start with is my time, but in seconds. So 3,600 seconds is, if we did 60 minutes in an hour times 60 seconds per minute, we will get 3,600 seconds. And I know that my current is 10.0 coulombs per second. That's another way of looking at that, coulombs per 1 second. I'm going to take my, my numeric value with the amps here, and I'm going to keep that with my coulombs on top. So my seconds will have canceled so far. And we're going to set up a couple more conversion factors here. So now I want my coulombs to cancel. So I'm going to say for every 1 mole of electrons that are transferred, I am using this 96,485 coulombs of charge. I know that for every 1 mole of my aluminum 3+, I need 3 moles of electrons to reduce that to solid aluminum. And last but not least, I want my value in grams. So I know that every 1 mole of aluminum, the same molar mass as the ion here, will be approximately 27 grams per mole. So if I was to multiply 3,600 times 10, then divide by Faraday's constant value, 96,485. Let's see, coulombs will cancel, moles of electrons cancel, moles of aluminum cancel. I'm going to be left with my value in grams here. So I will multiply across the top, divide. Don't forget to divide by 3, or else you're going to get more than you expect for your answer. So we should get about 3.36 grams of aluminum if we pass this current through 10 amperes for the duration of time of 1 hour.